So in the first lecture, what we discussed was the bonding from or sort of the buildup of atom to molecule and the fact that you get a bond between them. Now, carbon has the ability to make four bonds, but it doesn't necessarily mean it has to make four single bonds. It can bond to itself multiple times. So you could have, say, for instance, a molecule that's C2H2. All right. Now C2H2, if you're going to draw the Lewis structure, we would draw 1, 2, 3, 4, and then a carbon. 1, 2, 3, and there's our fourth one, and then our hydrogens. And what this has is two singly unpaired electrons up here, right? So what do you do about that? Now, there are two unpaired electrons. So the seemingly sensible thing is they pair each other up. This electron, because I'm just moving one electron, that's one hook goes there, and this electron, using one hook there, that just goes there, right? So if I were to just redraw all that, I could just put these two electrons here and here. And what we would end up with is, oops, that's the eraser. What we would end up with is a line here, here, and here, and here are sigma bonds, Then we have a bond here and a bond here. You have two bonds in between those carbons. And the first bond, that's just a regular sigma bond. But then the second bond, that's actually unique. That's a pi bond. That's what we call a pi bond. And pi bonds are higher in energy. And when you start stacking bonds on top of each other, you get these higher energy pi bonds, right? So you can go even further, actually, and just say C2H. You are probably thinking, what's going on? I say that because they drew that. That is actually C2H4. C2H2, that's what I'm going to draw now. C2H2, all right? So in this particular case, right, carbon still has a bond for hydrogen here, and there's still carbon here with a bond for hydrogen, but now those valence electrons are now all pointing this way, okay? So now you end up with a triple bond between the carbons and a hydrogen out here. Because the formula tells us exactly what we have to draw, right? These formula, in the olden days, you were able to determine what your atomic composition was by burning stuff, and then you could look at the spectra, you could look at the suit. There's a couple of old-timey ways people were able to use to get the relative number of atoms and their types sorted out. Now, once you get that sorted out and you know that for sure, then it's the chemist's responsibility to sort of model how these things would look, right? And so this would end up being a sigma bond, this would end up being a pi bond, and this would end up being a pi bond. So you've got two pi bonds in this carbon. And how does that look from a molecule point of view, right? So we had talked about these atomic configuration of carbon. Remember, we said carbon is composed of a very inner sphere 1s, inner sphere 2s, and then we said that had these three p electron orbitals, right? And when we filled them up, right, we called them, well, actually, let's recall, we actually even called them px, py, and pz, okay? And if we use this structure, if you remember back to how this made them look, these are three geometric structures. This is sort of like a lobe-looking thing, and we fill in the electrons. And the s orbitals, you'll remember, are just spheres, right? So if we draw the carbon, the inner one is just like a sphere. That's like a ball. Okay? We got a little ball. That's our inner sphere. All right? That's like shading to show that it's a sphere. That's probably not very well done. And then you've got the 2s, and that's an inner sphere as well, right? So that sphere actually envelops the inner sphere, right? So they're starting to get on top of each other. So the 1s is inside the 2s. And then the 3p, all right? What does the 3p look like? The 3p has an x orbital, so that's still, so your nucleus is still deep inside. Like your nucleus is like the inner bit, like it's all the way in here on the little carbon. It's all the way in there. And then the electrons just sort of start filling out space. And you get this p orbital, looks like that. And then that's your px, we'll say, okay? And then there's a px orbital, comes out the back, right? So, that's your px. Then you got your py orbital, and that sort of lobes out here, and that's sort of like that, and that's that we call py. Then you got one that's sort of like projecting out into the plane, right? And then that's your pz orbital. And then your electrons would start filling in here. You would have an electron, we'll just make the electron blue. So in carbon, oh, sorry, electrons are still going to be red, aren't they? In carbon, you got 2 electrons here, blump, blump, all right? And where do they go? You know, one of them is going to be occupied back here in this particular system by bonding to the hydrogen, okay? That's your hydrogen. And there's one electron associated with hydrogen and 1 electron associated with carbon. You know they're shared, right? So that can go that to the carbon, and this one could go to the hydrogen. It really doesn't make any difference. The electrons are not assigned to an orbital. They can freely exchange throughout these p structures. Now, this pz, all right, is going to be connected. So we'll say that this carbon is that one. This carbon is going to be right here, right? So we've got the same sort of inner electrons to S. So this is your second carbon. So let's actually even just label that's carbon 1. And then you got a carbon 2. Okay, and carbon 2, well, that also has the same sort of electronic configuration. It's got a py, okay, py, and it's also got a px, and that px is going to come over and lobe over here. That's also px, and it's also got a pz. Okay, so the pz, that's coming out at you. That's pz. All right, and just like in before, so this has a 2 carb, that's got an electron, we'll say here, and an electron, say here, and that's associated with your hydrogen. All right, so that counts for your first sigma, right? So that accounts for these 2 bonds. Let's just erase this up here. So we've accounted for we've made these bonds. We made all your sigma bonds. Now where do your pi bonds come from, right? So where do these 2 come from? These 2 that I've drawn in purple. Well, there would be a valence electron in this orbital and also one in your pz orbital, right? And these aren't being shared with anyone right now. So these are 2 are, these are your sigma. They're being shared just fine. These over here are being shared. Those are your sigma, and these are your sigmas over here. And now you got these 2 sort of hanging out in the space, right? And they're going to actually exchange through this space, right? So they're going to just sort of talk over here in these really high, they don't really, the way I've depicted them, they don't really touch each other. So they're a higher energy pi bond, right? This low energy with a sigma, that stable one, these orbitals have good overlap. That's a good strong bond. But these bonds out here, these are your sort of lower energy pi bonds, right? And this is what gives you your multiple bonds. Now, as you can imagine, I've said these are higher energy bonds, and we will learn more as we go on that these pi bonds are pretty reactive. You can get a lot of pretty terrific chemistry out of pi bonds. And pi bonding is a great way. So these ethenes, and we'll learn a bit more about nomenclature as we go on, but the names of these compounds change and the chemistry totally changes. So ethane, so this is right here, this molecule is called ethene. Ethane is just the same molecule, but it's got a single sigma bond. Ethane is flammable, but that's about the only chemistry it does. Like, it'll light on fire. Ethane will do all kinds of crazy chemistry with different metals. That these electrons, electrons are negatively charged. They're going to look for positive charges if they can find them. They're going to do chemistry. So these pi bonds, by virtue of that cool structure, are going to do some pretty neat chemistry. Now, you'll notice as I've drawn here, there are no other bonds. There's no place else to add electrons, right? So this pretty much means that you can have carbon with 4 bonds. You will be tempted, and I promise you, you will be tempted to do something crazy, like make a 5-bonded carbon, okay? No, don't. There's no place for you to put a 5. In fact, this carbon, even all the way out in the hinterlands of the Midwest. I don't know if that's really a Texas. We'll just say that's Texas. That's called a Texas carbon because it's big and wrong. Not that Texas is wrong, but it has its moments. And that's not right. Don't make a 5 bonds to carbon. So you're basically limited to don't, okay? That's sort of like no 5 bonds. You will make your professor sad if you make a 5 bonded to carbon, because we've talked about it now, and so we're all on the same page, right? You can't exceed valence, okay? So don't start. So you've got a nitrogen here, and you've got H, all right? 3 bonds, okay. You can, if you've got something, I said these lone pairs are negatively charged. If you've got like a plus charged thingy up here, and there's some sort of like electron interaction between these negatively charged electrons and that plus charge, and that gives you like a 4 bonds to nitrogen thing. Okay, that'll happen a lot. But what happens if you get like 5 bonds to nitrogen? No, don't do that. Also, make your professor sad. Okay? At least in OCHEM 1. If you go to graduate school, all these rules are broken. For various reasons, using superacids and all kinds of crazy stuff. But that's just as far as I'm going to say, this is also 1, 2, I draw a double bond here and then 3 bonds here. That's also 5 bonds. Okay? So all these pretty pictures actually paint a fairly compelling reason. You can't put 5 bonds onto this. There's no place. There are no more orbitals, and there are no more lobes, right? These pretty pictures really do a great job at helping us visualize what's going on. Now, for carbon and these atoms up here, that's a great rule, okay? No 5 bonds. Then you get down to these weirdos like boron, all right? And boron, as you'll remember, likes to have 3 bonds to it. Okay, so boron's is a silly guy. Boron, in its wisdom, just likes to have 3 bonds. Okay, and like nitrogen, which prefers to have 3 bonds and a lone pair, boron likes to have 3 bonds and an empty orbital, right? So this nitrogen has a pair of electrons just in its pz orbital, and it doesn't bond to anything, and it's quite happy that way. Boron is the opposite. It just likes to have a completely empty orbital, right? And like I said, that's not to say that these two things are innocent, because that is, after all, an empty orbital is just sort of a place where, I'm happy being alone. I'm self-coupled. But I guess I could get some electrons from something, right? And that would make boron go from a neutral molecule to a charged molecule. Like, just look at these two examples. This happens, right? I got a lone pair. I'm happy. Whatever. I'm missing a lone pair. Whatever. Let's sort of a marriage of inconvenience. Come here. Now, nitrogen now is going to say, all right, you can have my lone pair. Now, I've lost electrons, and that does kind of make me sad. That makes me positively charged. I mean, the electrons are still being shared, but they're no longer exclusively nitrogens. It's lost negative charge, and now it's positive. It's gone to boron, all right? And boron now is like, I'm pretty happy being neutral, but now I've got a bunch of negative charge associated with me. Now I'm negatively charged. And what you end up with is this charge species, okay? And you can actually do this a lot with all kinds of stuff, right? So moving electrons around is pretty straightforward as long as you keep track of it. Electrons don't evaporate, so don't disappear electrons, okay? Not like mafia, you can't just disappear things. And you can move electrons around, but when you do push them around, you gotta give them a charge, okay? So one of nitrogen, so if we draw that molecule that we drew in, whoa, that's a highlighter. If we drew that molecule we drew in lecture 1, okay? Or that's CH3, and then we had a nitrogen, and that nitrogen had 2 H's, and a lone pair. All right, now that's a lone pair. Now you're going to think back to your acids. An acid is, we'll say, a proton, right? HCl, remember HCl? So HCl, hydrochloric acid, this little jobby. All right, and HCl, you'll remember, we always like to draw it as basically just a proton, essentially, not really caring, and chloride being quite happy being negatively charged. Now, ammonia, so if, you got some, you read the news, you'll find in the production of methamphetamines, ammonia, so basically nitrogen, ammonia, which is just this, is stored, that's a neutral molecule, stored in a big tank. And every once in a while, some yahoo will try to extract the ammonia because it's used in the production of methamphetamines. Like, you can condense this gas into a liquid, and it's an important part of something called a Birch reduction that allows you to convert over-the-counter pharmaceuticals into drugs of recreational abuse. Now, every once in a while, this perfectly happy neutral-looking molecule will escape, and unfortunately, the person trying to steal this ammonia, which is a great fertilizer, will just get a face full of this gas, and their face will just melt. It'll burn severely. And the reason are these two lone pairs of electrons, because your face is made out of a bunch of organic molecules, and some of those organic molecules have hydrogens on them that those lone pairs can extract. And when that happens, it just goes like this, and it makes a salt, okay? And so when these lone pairs go and extract that proton, what you end up with is now the proton goes onto the nitrogen, okay? And the lone pair is now being entertained by this, right? And the proton follows it along, and you've created a salt. All right? You got a positive charge, you got to have the negative charge. All right, don't forget, positive charge always accompanies a negative charge somewhere, just like up here. Now, This happens, of course, this happens on that hillbilly's face, which unfortunately causes a lot of tissue damage. But lone pairs are terrific at extracting positive charges. And then when that happens, you don't have hypervalency. You still have an octet, right? So if we just sort of zoom in, if you will, on this nitrogen right here and look at what that looks like, you still have a nitrogen and it's still connected to, now it's connected to four things. It's got four things. It no longer has a lone pair. One of those things is, of course, still the carbon. And the others are now all hydrogens. All right? And the nitrogen itself is the thing that takes the positive charge, because the happy nitrogen now is, it's happy. There's nothing. Nitrogen does not mind being positively charged with a proton. In fact, it's probably slightly lower energy because a lone pair, that's a lot to deal with. You know, when it's bound to an electron, or when it's donating that lone pair into a proton that would otherwise have nothing to do, it's happy, you know. And plus that positive charge has got a negative charge over here. It's got a chloride. So, you know, this is great actually. You can, this becomes a solid. You can put this in a bottle. You can store it on the shelf forever and ever. Okay? Basically forever and ever. This, that's a gas. That's tough to keep in a bottle. But this is a solid. It's now a salt. And it's super stable. Both are stable. It's just in the presence of an acid, that lone pair makes it super reactive. This, as you can imagine, of course, if you go back to CHEM, there's a backwards process in which if you have, say, a base, you can go backwards. So an acid will take you to this, if you have a base like sodium hydroxide, that hydroxide will come and take one of those protons and it'll make water, H2O, all right? And the sodium will pair up with chloride to make table salt, sodium chloride, and you'll get your gas back. It'll evolve back as a gas, released into the atmosphere. All right? So that is how you can get formally charged structures. Now, what's particularly crazy about organic molecules, particularly organic molecules that have pi bonds, all right, is, as I keep saying, the electrons belong to nobody, right? As I come up back here, these electrons don't necessarily belong to anybody, these ones in purple. They you know, are unto themselves. This electron is quite happy. Both of these electrons, for some reason, for some amount of time, both want to end up over here. I mean, that's probably just fine. They won't, because both of these atoms, you know, carbon 1 and carbon 2 are like identical. So why would an electron prefer one over the other? And in this particular case, I really can't give you a good justification because there is none. The electrons, they're identical. Now, if one of these carbons weren't carbons and had more property, what you probably remember is electronegativity, they would want that electron more. So remember what electronegativity is, all right? Electronegativity from your Gen Chem days basically says that as you move down the periodic table, these atoms just want electrons more, and that's pretty clear. They're happier with having more lone pairs that really sort of they hang out. But you know, if you say have a carbon fluorine bond, this fluorine is going to try to suck up as much carbon's electrons as possible. That's a covalent bond, but it's not very equally shared. It's sort of Orwellian. Some animals share, and some animals share more than others. And in this particular case, that's what we have here. It's just simply unequal sharing. So when we draw a bond, like say CF, which I'll just draw it right here, CF, that looks pictorially no different than that. But the reality is, like, most of these electrons are over here. They're both over here for the most part. Whereas here, these electrons are like here, they can be over there, they can go over there. They bounce back and forth pretty much freely. There's really no difference. So that has some pretty profound effects. In the sigma bonds, those are low energy, those are core electrons, but the pi bonds really feel that inequity a bit more. And so when you have a system like, keep my color codes consistent. When you have a system like formaldehyde, okay? So formaldehyde is CO. And then it's got H, okay? Now, if you draw the Lewis structure for that, what you'll end up with is a double bond between the carbon and the oxygen. There's really no other way to do it. And then two lone pairs on the oxygen. Well, oxygen has two lone pairs. Nitrogen has one, fluorine has three. You can come back up here and look at your little image. So you only got two individual unbonded electrons. If you look at this, for what we have here for carbon, you can imagine putting in one electron for nitrogen and then one for oxygen, and now you see you start to even pair up electrons, and now you have two places where you can start throwing in bonds. So that's your oxygen molecular orbital, okay? So oxygen now having that's nitrogen still. There, that's carbon. Now oxygen in this configuration is more electronegative, right? Scroll back up. Hope I'm not giving you a headache. Oxygen is on this side of the periodic table. That means that we're going to have some unequal sharing of that pi electron. It's going to want to be over there on oxygen. So when we draw this bond, and I'm going to draw just sort of a simple truncated version of this. So we're just going to do a quick zoom in. You're going to see a carbon, and we've got a bond here, and we can draw an oxygen. And if we were to just draw it like this, no one's going to tell you that that is wrong. And the reason no one's going to tell you that's wrong is because it is correct. How's that for some logic right there? Right? You still have an octet, okay? You still have 1, 2, 3, 4, 5, 6, 7, and 8. Because one of those is on carbon still, electrons around oxygen. Now, carbon only has 6 electrons, right? So it's got 1, remember, there's an electron that forms that, there, right? It is actually given one of its valence electrons up to this negative charge, okay? And I can even draw these as two distinct charges, right? One of its electrons is now over here. It is what we'd say not sharing that electron very equally, since that valence electron from carbon is over here. But still, all 4 of its valence electrons are involved in bonding, so this is actually a perfectly correct structure. They both are, and that's what's going to kind of freak you out a little bit. These structures are the same. They're what's called resonance structures. And this is sort of where our line drawings break down, okay? I can't actually draw a picture of formaldehyde that represents both of these cases, with this being a slightly more realistic depiction. Not 100% realistic. This electron, every once in a while, can still sort of make its way back to that carbon and giving you more of this representation than that one. The truth is, as they say, somewhere in between. It is not true to say this is correct all the time or that's correct all the time. The truth is about resonance structures is it's really a limitation on our ability to actually draw what's going on. We can maybe draw something a bit more complicated, like there's a carbon here, and then there's an oxygen here, and then the actual electron density more or less looks like this, where you're more likely to find an electron sort of over here by the carbon, and of course you'll find a little bit of electron density out by by the hydrogens on this from your H. Those will be there, but this is sort of like, I don't know. It's how I guess I would draw it, but that's really cumbersome. That's really awkward to draw. So we're never going to draw it like that. We're always going to draw formaldehyde like that, like this. All right, and we have to be aware though that it is actually more like this. And what does that mean? Well, that means that has actually some pretty profound effects on the kind of chemistry that something is going to happen. Because if you have something that has a lot of electron density, like say a nitrogen, nitrogen, as you'll remember, has 3 unpaired electrons in its p orbital. 3 unpaired electrons gives it a lot of negative charge, and as we just discussed, it really likes to attack things. And if that carbon is indeed basically positively charged, then those lone pairs are going to see that positively charged carbon and this negatively charged oxygen as an opportunity to unload some of those electrons, which is going to give it an impetus to go and attack that carbon, all right, as a positive charge. And then you end up with something as a carbon and an oxygen, and now the nitrogen has lost its electrons, and now the nitrogen becomes positive. This carbon still has hydrogens, and then the oxygen is still negative. And this is the very fundamentals, the foundation of organic chemistry. It's all in the electrons, okay? Everything I've shown you is just electrons sort of moving around. You push electrons to one side and you expose the nucleus and make it a little bit more positive. That means that formaldehyde is going to do this sort of chemistry where nitrogen attacks it, right? This reaction, as you can imagine, is going to be way less forward on carbon double bond carbon, right? There's no electron difference. So if we drew our electron cloud, we would have like basically the electrons have an equal probability of being here and here. And then also on the hydrogens. And so if you're a nitrogen, this nitrogen is going to be like, well, no, that's too much. No, there's too much electrons there. There's a lot of electrons everywhere. Never mind. It's going to go away. No. No reaction. So nitrogen is not going to attack that. There's just electron density everywhere. How's it going to get to a nucleus? How's it going to get to the positive charge? That's what the nitrogen lone pairs want. They want the positive charge. They don't want all the dumb electrons all over the place. So that is basically your fundamentals of how organic chemistry is going to work. And I kid you not, it's all electrons. And as we're going to learn in the next lecture, it's all acid-base. Because actually electrons are something that has electrons as a base. It's called a Lewis base. So the Lewis structures, probably learned that in Gen Chem. We'll focus on it more in lecture 2. Takeaway from this lecture: electrons dominate OChem, okay? And it's the electronic structure of carbon really that sort of gets you there. And this is really found in resonance forms, and orbitals. Orbitals. And we kind of cover the topics of sigma and pi bonds. I've run out of space. Orbitals. And we discuss sigma and pi bond, those two orbitals, and how sigma are low reactivity, pi are higher reactivity. All right.